Good morning. This is the Neuroscience as a STEM subject workshop. My name is James Olson, and I'm the character on the top there, but the name on the bottom. And Dr. Schwartzbloom in the back is going to give a little presentation later. The subject today is looking at both sensory and motor systems, which is basically the main components of our central nervous system. The central nervous system takes in input from our senses, processes it in some way, and then produces some output, so some motor action. What I'm going to start with is the sensory system. That's where the system starts. That's where we get information from touch, from sight and sound. And I'm going to talk about this character on the screen here, which is called the Homunculus. It looks somewhat human, but it's basically out of proportion, and you'll see why that is, why it's not quite in the proportion that we normally would think of. A year and 1 day ago, there was an announcement by President Obama of the Brain Initiative, which is sort of the next Apollo project. It's the next genome project. It's there's a number of components of that, but one of them is to create what was called the connectome. It's how all of our 100 billion neurons make their 100 trillion connections, how each one of them goes. Now, normally when I teach neuroscience, and we bring out a human brain, or we look at an example like this, it looks random to some degree. All of these bumps and convolutions and gyri and sulci, and all the neurons that are in there, how can we ever imagine how to connect them? And I think everybody's first thought is that it looks something like this. If you looked at all the wires in there, it's like what it looks like behind my desktop computer. After I've connected, the VGA and all the USB ports and the power, it's just a mess of things. Fact is, it's not like that at all. It looks, if anything, if we would have an analogy, more like this. Things are in nice order, not only from place to place, but within the region that they're going, things line up very, very nicely. And the best way of seeing that is it turns out to be in the sensory systems. I'm showing you this guy here, Wilder Penfield, who was one of the first ones to recognize this and to really study it. So this rather nerdy-looking character, this is when he was playing rugby at Princeton. He went on to become a neurosurgeon in Montreal, and one time was described as one of the most famous Canadians. He became a neurosurgeon, and as part of the treatment for epilepsy, would take out parts of the brain that had the epileptic focus. But he didn't want to take out parts that were still good, so he would stimulate parts of the brain while the patient was awake, but with their brain exposed, and ask them what they felt. And because by doing that, he could see what parts of the brain the sensory systems were connected to, what parts of the brain, when he would stimulate here, the patient would feel something in their arm or in their leg, and make a map of the body on the sensory cortex. Now basically the brain, if we start by looking at this mapping problem, we can divide the brain into these two specific functions that I mentioned, motor and sensory. And with the graph on the left here, that dividing line pretty much for the cerebral cortex makes that division. Everything in the back side of the brain, which is towards me, is sensory. Everything in the front side of the brain is motor. So that's the big map. We can then start to divide up these sensory areas into some of their major, where the major sensory organs first have their connections. So there's a auditory area, here on the temporal lobe, the primary visual areas in the back and the occipital area, and the somatosensory, which simply means body sense, is on the parietal area, sort of from the center on either side. So that's the big map, sensory motor. We can look at maps of each of the regions, each of the major sensory modalities, and then we can start to divide them up more and see within those regions, how are the individual sensors mapped. Now for our vision, the main sensors are on the retina, and through a one relay circuit, they end up on the cerebral cortex map. And we can find where the macula mapped, which is the main area of our vision, is what we focus on. And it's the area that has the highest density of photoreceptors. So that's where our visual acuity is the best. And when we look at it, when we look at how that's mapped on the cortex, we find that is the largest area. That's a large area. It's disproportionately large. So that tiny little macula in the middle of your retina maps into a very large area. Same thing can be true of the auditory system, although in this case it's not mapping a visual space or a two-dimensional space, it's mapping the tones. And this is the way it looks like. Again, on that temporal cortex where the primary auditory area comes in, we have the tones from 500 to 16,000 hertz. And the students I talked to go up to 20,000 to 25, I guess. Nevertheless, you can see this is not mapped out proportionately either. The 500 to 1,000 hertz takes as much space, 1,000 hertz, as the 8,000 to 16,000. So we have 1,000 hertz at one end and 8,000 hertz on the other end. There's a disproportionate mapping of the low frequencies. And why do you think that would be? Because of voices, yeah, because when we communicate, I'm speaking in a lower register, around 500 hertz, or actually somewhat below that. So when you hear the concertmaster tune up the orchestra, what tone does he play? Any musicians here? 440, which is the concert A. Right, so that's somewhat at this end, and that's where all of our music is, and it can stretch up a little bit further. All right. So what about this primary somatosensory area? How do you think that's going to be mapped? With the idea that what we're interested in is where's the most density, highest density of receptors. What would have a bigger representation? For example, my hands or my arm? My hands, right? Because I have an incredible sense of touch in my fingers. I can put my hand in my pocket and I can tell the difference between a nickel and a quarter. If I put it on my arm, I have no clue, right? Because I have greater receptor density. So what happens when we map the somatosensory system, our touch sensors, onto the somatosensory cortex, we get this homunculus kind of character in two dimensions here, with a large representation of the hand, a large representation of the face. And arms and legs, not so much. Trunk, not so much either. So what's important, again, is when this mapping takes place, is what is the receptor density? And that will map that area of receptors onto that area of the cortex. So it's not surface area, in other words. It's sensory receptor density. The way we're going to test this today, and this is where we get to the hands-on part, and I'll turn the mic over. At least make these little implements of torture, if you would. But there are little points on a card that have a specific spacing. And this is a tool that a physician may use if they're assessing if you have a spinal cord injury. They'll look to see if you have similar sensation on each side of your body to determine where your lesion might be. So they'll press these points on your arm or on your finger or on your head, and they'll ask you, do you feel one or do you feel two? And what I've done here is created some of them with two points at known distance apart. And then I have the 1 point too. So the idea is that you'll switch between, when you test this, you'll switch between doing the 1 point and the 2 point and see if your patient is consistent. If they're giving you the same response each time, you know, it's a 50-50 guess each time, 1 point or 2. So you want to give it a few tries. The way this will work, you'll make these little cards with tape and toothpicks and a ruler. And then one of you will be the patient and one of you will be the examiner and try it on each other. 2 caveats I'd make is don't press too hard. We're not trying to get blood. And in fact there are different sensors for pain and for light touch. So there's a variety of sensors in your skin. Not only different sensors, but they travel in different pathways in the spinal cord and they end up in different places in the brain. And again, so this is the example. These pictures are in your handout too. Head, torso, arm, hand, leg, and foot. And then what you can do at the end is, if there are these cutouts of the homunculus characters, you can make your own, and you have your own personal homunculus to take home and show your kid or your spouse or whatever. I would add at the end here that this is pretty much an adaptation for the classroom of this website, www.maxplanck, and this reference is in the handout too, so you can go and take a look at that. But they have an online version where if you put in the different spacings that you measure, they'll create this character and you can download it and use it as your Facebook icon or whatever. So what we're doing in this workshop is using a 2-point discrimination tool to map the density of receptors on our skin. And from this we're projecting what that map would be on the cortex of the brain, in the somatosensory cortex, and creating a homunculus, which is sort of this description of that sensory map in 2 dimensions or three dimensions on the brain's surface. So there's 3 steps to it. We create these cards, which are our 2-point discrimination tools, and then we'll test them on different parts of the body, on our fingers and arms, legs, head, and then we predict what size that is going to be mapped onto the brain.
I've been looking for something like this for a long time.
And what's nice is that they're sized. They're
Yes.
pre-sized for this.
It's fabulous.
They do have a kit available. They do have a kit available.
Well, he thinks they do.
You have it. We did this obviously correctly with this.
Measure perpendicular to the tooth.
Oh, well, then I did that wrong.
Illustration.
Here there's sort of a step-by-step project. You make the card, you test it on each other, and then you'll make your little homunculus creature out of the cutout. You don't have to worry about getting an exact now, because when you fix the second card on the top, it really tightens them in.
High school. I actually teach a neuroscience student for biochemistry course.
I piloted this in the high school.
Okay.
Or did it? No, that was 2. No, you had 2.
We're a little confused about the data, but I think she got it cleared up. What are we exactly recording?
You want to record the distance that you can determine you have 2 points.
Okay, so if she does all, then what do we record?
Then you use the smallest one.
Okay, and then so you go down consecutively.
Yeah, right. And you can switch it off. You can try to make sure that they're.
Then how hard does she have to press?
It's light
She's
touch.
been really light.
Yeah, it's light touch. It is light touch.
1.
That was, yeah. Yeah. You got this one. You were kind of this one lower for your getting.
Oh yeah, I was afraid to say it.
You're guessing. You're thinking. You're kind of like psyching yourself out too. The other thing that's going on.
As I say, it's a
Like, I don't dare call it a 2. You know.
It's a 50-50 chance each time, so you switch back and forth.
Yeah.
Look for consistency and repeatability.
You can actually use this. It felt kind of like 2, but I don't know. It felt like a wide 1. Definitely 2.